This is the 32nd lecture on a course on heuristic search. And in this lecture, we're going to continue where the last one left off, looking at inconsistent heuristics. And what we have historically is the first real notion of what could go on in inconsistent heuristics. So we're talking about inconsistency. Was in 1977, there's a paper by Martelli. And Martelli showed that there were issues with inconsistent heuristics. He showed that there could be an exponential number of re-expansions. And this work actually comes out of, he shows a transformation, but it comes out of earlier work on looking at graphs with negative edge cost. So running Dijkstra's algorithm on problems with negative edge cost. And he shows that there is there's a relationship between the problems there. And then he was able to take existing work that looked at what could happen in a graph with negative edge cost and show the same thing happens when we have inconsistent heuristics. There's roughly a correspondence between inconsistent heuristics and negative edge costs and the types of things that happen in those spaces. And so he looked at that problem, and then he proposed actually an algorithm. So the example that we went through in the last video comes from his paper. And then he proposed a new algorithm that was going to try to solve this problem. And he called this algorithm, well, let's try and think about it. We have algorithm A star, so why don't we have algorithm AB? And the idea behind the algorithm B is essentially to say we want to not let the F cost decrease. And when the F costs decrease, we're going to take a repair step that is going to be trying to be consistent and sort of avoid the inconsistencies. And so one way that you can think about algorithm B, I'll describe it in a different way briefly, is that basically we can, in the worst case, we can think about every time we expand one new node by F cost, we'll go back and expand every node that we've expanded so far from low to high G cost in order to repair any inconsistencies that have been discovered when we expanded by F. And he does this in a slightly different way. So if we were to write A star out from a regular perspective here, then what we'd see is we're just going to add a couple steps to it. So normally what we do is put the start on open. And then, we're going to set the G cost to be 0 and the H cost to be, so init start, the G cost of that state and the F cost of that state. And then we're going to say if the open is empty, then we're done. There's no path bound, so we'll return failure. And then we're going to look at an additional step here. So what is our normal step? We're going to say remove lowest F from open. And we'll call that state N. Step 4 is going to say if N is the goal. Then we return the path from start to N. Otherwise, we're going to expand N, and then and we're going to get the successors, N of I, whatever they happen to be, and then 6 is going to be add N of I to open or closed, depending on whether we have shorter paths or not, or whether nodes have seen before. But we do have the option here that we didn't think about before of saying that when I find a shorter path to a state that is on the closed list, that we will re-expand that, or we have the potential of re-expanding that state. Well, if I do find a shorter path, I will expand it. So this is A star as we normally see it. And there's 2 extra steps that are put inside here by algorithm B. So we'll put that in blue here. What does algorithm B do? 2 different things. It's going to have a capital F. It's going to start by initializing F to be 0. And then here, there's going to be a new step right here, which is for all nodes with f less than f on open, expand from low to high G. And this is what's important here. Okay, so what algorithm B does, it says, look, I'm going to keep track of f. Oh, sorry, there's one more step I forgot in here. Else, so I went back to black, get back to blue here. Okay, so else we're going to say f gets f of n. Okay, so when we choose a state to expand, so we're going to remove the lowest f. And if there is a node with f less than f, capital F on open, so basically capital F is the highest f we've seen so far. If f drops, then we're going to start expanding states from low to high G cost. So we're basically going to run Dijkstra's algorithm for all these states that have f less than f. So capital F of n less than capital F, which is the maximum f we've seen so far. And otherwise, we're just running regular algorithm. And so this algorithm works very well in practice. And let's take a look at what happens here. And what I'm going to do here is, just as before, I have a, oh, I thought I had it here. I wonder if it's still sitting here. Okay, I'm going to pause it. And I'm going to go get the example that we had from before, and I will put it into these slides. So here we go. Okay, and we are back. Here's the example that we were looking at previously. And what we're going to do is we're going to try and look and see what happens on this example when we use Martelli's algorithm instead of using A star. And so what we're going to start out with is we're going to start out with A on the open. So we're going to write here our node. I'm going to use blue just so we know that we're using Martelli's algorithm, F, G, and H. So we're going to start with A here with an F cost of 23 because the G is equal to 0 and the H is equal to 23. And now what's going to happen here, this is really interesting. So what we're going to generate is we're going to put on the open list B, C, D, and E, as we did before. This is expanded first. And B is going to go on with a G cost of 1. C goes on with a G cost of 6. D goes on with a G cost of 9. E goes on with a G cost of 11. And the H cost of B is 13, 7, 3, 1. And then what we're going to see here is 14, 13, 12, 11. Okay. And what's going to happen here is when I do this first expansion of A, I'm going to set F is equal to 23. So what does the rule now say? It says for all nodes with F less than F, expand from low to high, G. Otherwise, I'm going to update my F cost. So what I'm going to do is I'm going to go on to the open list, and now the key thing here is I never am going to actually expand new nodes that I haven't done before, but I'm going to look inside here and I'm going to say expand these states from low to high G cost. So the first node with lowest G cost is B. So I'm going to just use a slightly different shade here to say this is the re-expansion phase. So 2, I'm going to expand B because it has a G cost of 1. And when I do that, I'm going to update the G cost of C to be 2. And I will update D and E as well, but I'm not going to show that here because next I'm going to expand. I'm ignoring the heuristics now, so I'm going to expand C. When I expand C, I'm going to update the G cost of D to be 3. So there it is, cost 2. I'm going to expand D with cost 3, and then I'm going to update the cost of E to have a cost of 4 here. And the next node I'll expand is E with, so I should update the F costs here. So when I do this, I started out with, I started out here. This is still going to be 13, but this is going to be 9. This is going to be 6. This is going to be 5. And now what happens? Well, now I'm back to continuing my search, and I'm going to generate G here with a cost of 5 with a heuristic of 0. My F cost is going to be 5, and therefore I'm going to expand that 6th. Sorry, I'm going to generate G. Sorry, got the cost here right. So the cost of G is going to be 1, 2, 3, 4 plus 19. Okay, so 19 is my G cost, 19 is my F cost, and I've expanded everything else. I don't have any shorter paths. So now I terminate with a, oh, I did this again, sorry. Okay, so it's 19, I have to add the 4 into it. 1, 2, 3, 4 plus 19 is 23, and it's 23, because the original heuristic is admissible here, and so 1, 2, 3, 4 plus 19 is 23. Okay. So just by doing this step of looking at the open list here and doing the states that are on the open from low G to high G is immediately able to repair this so that we do a linear number of node expansions in practice. Okay, so this is great. On this problem, we went from an exponential number of node expansions to a linear number of node expansions. We expanded every node exactly once. And the question is, does this solve this problem in general? And the answer is no, it doesn't. And so what we can see here is if we were, for instance, to make a very, very small change to this example. So the only change, in fact, what we see here is the reason why this works is we have a very high F cost right here coming from this high heuristic. And then everything else is lower than that. So we just do it all using Dijkstra's algorithm, basically. And so what we could do here instead is if the heuristic, so we have a linear number of expansions on this particular problem. We did every node exactly once. And that seems really good, but we might ask in practice, is this actually, always going to be the case? And what we see here is we actually hit this highest F cost immediately, and then all these other nodes had lower F cost. So this high, very accurate heuristic here is actually providing the information that allows this algorithm B to have good performance. And what we can do instead is if we actually just take exactly this example and we make this heuristic to be 0, then what we're going to get is we're going to get to an n squared performance. And for the sake of just sort of the roteness of going through this example, I'm not going to show step by step what goes on here. But what I can show actually is I can show what happens here on an abstract graph. And so let's just look at some of the numbers here of what is going on. So let's switch over to this window. Okay, so we transition over to this problem. And what I'm going to show here on this problem is we'll just see what happens. Again, you can run this on the web demo. We're going to see here we've added capital F. So what happens here is we do A, we do E, and then we're going to do D. Now and what's happening here, so we do D, and then now we're going to find you see the F has gone up. Now E is going to have a lower cost, so we're going to go ahead and do E. So we do D, and then we do everything we've expanded before, we do E, and now we're going to continue. So now we're going to do C as a new node, and then the Dijkstra step is going to go D and then E. And now we're going to expand B for the first time, and then C, and then D, and then E. And then at this point we're done, so we go to G and we finish. So what we see here is the first time we do E, we expanded, and then we do D and E, and then C, D, and E. And generally speaking, what's happened here is we'll do 1, and then 2, and then 3, and then 4, and then 5. We might do up to n re-expansions, and so if you add those up, that gives us n squared. And so that is where we're actually going to see a behavior here, which is n squared. And practically speaking, if we think about this, what can happen here is that for every new node that we expand, that new node may have shorter paths to other states. And so by doing a Dijkstra step of re-expanding all states, then what we can see is sort of every time we get one new node, then we could see all re-expanded. So this is going to be the pattern. So we do 1 and then 2, all 3, followed by all re-expanded, all the way down to the nth expansion. And so this is going to be, we have n total steps here, and each step is all nodes re-expanded that are necessary expansion. So that's sort of n nodes is the maximum we could get here. Each of these can be at most n. and there's n steps here, so overall this is going to be O of n squared. Okay, so this is again the worst case, and you know that can happen in practice, and actually it can happen in practice with real problems. We'll get a chance to talk to them a little bit later. There are then, if you go onto the web page, sorry, there's another example of a problem that shows this a little bit more clearly. And what that problem looks like is something where you have a bunch of nodes across here. We have many paths that go through sort of this middle region right here that then go down to a region down here. And you basically have approximately n nodes here, approximately n nodes down here. And every time we do one path on the top, then we end up doing some number of nodes. So we do one path on the top, we do one node. We do the second path, we do 2 nodes. We do the third path, we do 3 nodes. We do the fourth path, we do 4 nodes, and so on until we've done n squared overall. And the reason why this example is a little bit more interesting is we can see here that we can see exactly where this comes from. And in the previous example, we had this really high branching factor, and we actually had an exponential range of costs. In a problem like this, when we do this, we don't have to have this exponential range of costs. We can have a much smaller range of costs and still get this n squared behavior. And so anyway, so this is this. And there was one other class of techniques, though, that have been proposed to try and fix this problem. And there's sort of an older version and then a newer version of this. So Merrow, in 1984, looked at the proposal of this idea of having modifiable heuristic estimates. And so he asked the question, what could we do if our heuristic estimates could be modified? Okay, so the question is, what can we do if we modify the heuristics? Up until now, we've assumed that our heuristics are always the same. And now we're going to think about modifying them. Oh, I do want to say one thing I did forget to say up here. So Martelli did one other really important analysis here. He asked, is there an optimal algorithm? That is, like we have A star, which is always going to do perfectly well with a consistent heuristic. No algorithm can do fewer necessary node expansions. There's some tie breaking, but ignoring the tie breaking, you cannot beat A star without additional information. And so what Martelli proved is actually when you have inconsistent heuristics, there is no dominating algorithm. You cannot have an algorithm that is guaranteed to do, which is guaranteed to do far, less than any other algorithm. And the reason for this is that we could expand a state that's not a necessary expansion. And when we do that expansion, we might discover a very large heuristic value, which might tell us some information that we wouldn't know otherwise. And so actually we'll see this here when we look at Merrow's work, a little bit of how this can happen. Okay. And so Merrow had a couple of rules. He introduced the idea of Pathmax. And we're going to look at what these Pathmax rules are and what they are able to tell us about what goes on in the search. And I'm not going to write down the precise rule. Well, I could write them down, but let me show you because it's a little bit easier to see the Pathmax. And then we're going to get to a later thing, which is called bidirectional Pathmax, which used for undirected graphs. So Pathmax has 3 rules. The first rule here says that if I have a state with a large heuristic value, so suppose I have a heuristic of 6, and then I have 2 children that have heuristics of 3 and 4, then what I can do is if I'm allowed to modify my heuristic estimates, I can take this 6 and I can propagate it to the children and say, the children don't really have a heuristic value of 3 and 4. Oh, sorry, we're going to assume edge costs of 1 here. And notice this is a directed graph. Is what we can say is, well, their heuristic costs are actually going to be, so I'm writing the heuristic inside the node here. Because I know that this heuristic is admissible. If this is 6 steps away and I took 1 step, then now I have to be at least 5 steps away. And so both of these, of course, now can be raised to be 5. So that's the first Pathmax rule. The second Pathmax rule says this. Suppose that I have a state here with a heuristic of 3, and I have 2 children. One child has a heuristic of 1, or sorry, they both have edges of cost of 1. One has a heuristic of 7, and one has a heuristic of 4. What I can say here, so this is the new value, is I'm going to get to a new picture here, which looks like this, which says, look, if this state with a heuristic of 3 move and it reaches either a state that's 4 away or 7 away, then we know, and this cost 1, we know that here we actually have to be farther away. We could actually have to be at least 5 steps away. Because if the path through 3 goes to 7, then we're 8 steps away. If it goes through 4, then we're 5 steps away. So what we're going to write here is we can increase the heuristic to the minimum of the child plus the edge. Now, if this edge was 20, then the minimum of the child plus the edge would actually be 7 plus 1. And in this case, it's 4 plus 1 is 5. So we're going to change that to be 5, and we leave these to be the same. Okay, and so that's the new problem that we're going to end up here. This is rule number 2. And there's a third observation that we can make, which is if we have an undirected graph, BPMX, then what we're going to say is suppose here that I have a state with 3 that has a child with a heuristic of 6 and another child with a heuristic of 2. We can actually take this and convert this, because this is an undirected graph, then everything can be a parent of everything basically. So 6 says that the parent has to be at least 5, and this other child has to be at least 4. And this observation comes from some work by Ariel Fellner, where he was doing, compression on heuristics and things like this, and he ended up getting inconsistent heuristics. And when he got an inconsistent heuristic here, what happened is he realized that maybe I go down the left branch and I get a very large heuristic. I go down the right branch, I get a very small heuristic. And if I just were to say, propagate this heuristic up and then back down, maybe I don't have to go down this right branch here, or I don't have to go as far down that right branch as I would have otherwise. In particular, what can happen is sometimes you can get a very large heuristic value here, which cuts off this state and cuts off others as well. So Pathmax is a second technique. First, the directed graph version, which is these two rules here. This basically says that the children get the parent minus the edge cost. There should be a 1 here. And then this one says that the parent gets the minimum of the two children plus their edge cost. Okay, so those rules, we can apply them to some of the examples we've done before. And for instance, we will see a great reduction in the number of node expansions. But if we go back to, so in particular on this problem, we'd see even further reduction in node expansions because we'd be able to propagate heuristic values. In particular here, what we'd see is that because there's an edge cost of 19, I can immediately update E's heuristic cost to be 19. And that's going to immediately allow us to start propagating values back. So we're going to do much better. But in examples like the one that is available online, I'm not going to go through all the details here, then we can see that it isn't always guaranteed to fix things, only sometimes. And so we can look at if we look at these techniques, then actually in practice, then they may be able to speed things up, but they're not always guaranteed to speed things up. And so we can find, there's a video actually on the Moving AI website. I'll see if I can put a link to it below that shows what happens that on an actual problem, if we're using BPMX, then BPMX is able to recover basically the inaccuracies in the heuristic. And we'll talk about the ways this can occur from actual heuristics a little bit later in the class, not too long from now. And so there's some interesting results that we can think of by looking at if we look at, for instance, the minimum change in H cost. So if we think about the minimum change in H cost, that's going to help us bound how many times we can reopen a state. Because every time I take a state and I reopen it, when I'm thinking about my inconsistency here, the inconsistency what actually goes on is that we're lowering the F cost of a state we've expanded before. So let me show a couple of things here, and then we'll talk about what can happen. So the question is, what is the cost of BPMX? And then we'll look at overall what can happen. And BPMX can be put into IDA star, it can put into A star. Particularly the difficult thing is when we try to put it in A star, there's a question of how much propagation we should do of heuristic values. So if I have a state space, let's just say where I'm going to have my heuristic values inside here are going to go 0, 2, 4, 6. And then I'm going to have the goal here, the heuristic of 0. And I'm going to have edge costs of 1, 1, 1, 6. So you can imagine here, somehow I have inconsistency. Oh, do I have inconsistency? Well, actually, I don't have inconsistency here because my edges are, my difference in my heuristic is always less than my edge. So I do have inconsistency here because the change in the heuristic is 2. But this is actually, what it's doing is it's causing the F cost to go up. So if this is a directed graph, it would be okay. As an undirected graph, it's not okay. Then I wouldn't have a consistent heuristic. But what's happening here is that, like, as I get towards this state, you can think about I'm learning more and more about the heuristic, and so I'm getting more and more accurate. So what happens here? Well, what would happen is I would expand this first state, and then I would propagate the heuristic back through all expanded states, and I do one propagation. And then I would expand the next state, and I can propagate the heuristic back because now I can make this state have a heuristic of 3 and that one have a heuristic of 2. So I'm going to propagate back through 2 states now. When I come to here, then my 6 can become 5 and then 4 and then 3. So I can propagate it back through 3 states. And then at this point, I'm done. But in general, I could create a line of states like this, where if I were to propagate my heuristic values all the way back through these states, I would actually do n squared propagations. So this is worst case. Is, we can be precise, theta of n squared re-expansions. Okay. But we can create examples where, for instance, I find a heuristic that is large enough to allow me to basically immediately terminate my search and save a massive amount of node expansions. And so all I have to do for this is I have to, we can think about this, you could think about this in general. I could have an algorithm that actually just expands a random state, happens to find a heuristic that's very large, and then it's pruning a lot of states off. There's other examples what we can do. So let me show it. Actually, I'll just switch over to a picture of this. And let's take a look. So here's an example where we can get some really good savings. And what's going on in this example, on the left-hand side, if we don't do BPMX, then on the left-hand side, we may go down and expand a very large range of states down there that all have heuristic of 0. If I, though, go ahead and expand node B and do the bidirectional Pathmax propagation, then I can propagate heuristics to all those states. And what I'm going to discover is that all of them have the same F cost as the goal. And since I do have the goal available for expansion, I'm then able to terminate. We can create other examples where, if, for instance, if I do one node expansion that's just extra, that isn't strictly necessary, behind that node we can find a whole bunch of information. And this actually what makes inconsistency very hard, because what it means is that there might be some nugget of information that it's just hiding behind a state somewhere, that if I expanded an arbitrary state, I might find that information, and it might cause me to get massive savings in the number of node expansions that I need to do. And so this is why this has sort of been a hard problem, but people didn't work on it very much because in practice, we didn't seem to have this happening. Okay, and so what we're going to see is that it ends up that there is something we can do that's going to be even better than this bidirectional Pathmax, because the bidirectional Pathmax might help, it might hurt, but we don't know either way. And There's another thing here which is worth mentioning. So this is good versus bad inconsistency. So bad inconsistency is inconsistency that basically is misleading to the goal. And so if we go and we look at this example back up here, what we see is that the optimal path to the goal has the largest heuristic values. And the suboptimal paths to the goal, all the different suboptimal paths, have high path costs but low heuristic values. And so here, this inconsistency is 100% misleading, right? It's taking us down exactly the worst path to the goal, and then takes us down the second worst path, and then it takes us down the third worst path, and then the fourth worst path, and so on. And so, so this is bad inconsistency. It's misleading. But there is a type of inconsistency which is good. And this is something like, it's basically using a variety of values. So you can imagine that when I have especially when I have a pattern database, for instance, with one pattern database, I might be able to use duality or symmetry or other techniques to actually get many, many possible heuristic lookups from a single pattern database. And I might be able to build multiple pattern databases that also give me many values that I can look up. And so in practice, what I'd want to do is I'd want to take the max of all of those values. So but in practice, of course, every heuristic lookup is more expensive, and the marginal gain that I get from doing one more heuristic lookup is generally going to be small. So if I have a rich set of heuristics and I take a random of a mix of informed heuristics, what's happening here is that just by taking, for instance, one random lookup, or maybe 2 or 3 random lookups, if I have 10 or 15 possible heuristics I could use, I'm reducing the overhead of actually looking up all possible heuristics. But so that cost of the heuristics is reduced. But I'm going to slightly degrade the quality of the heuristics that I'm going to get. And by taking a random heuristic, I can get a less informed heuristic in practice. And so a less informed heuristic is going to be, so that's not as good as a more informed heuristic. But the thing is that if I have many different heuristics and I randomly choose them, then within a short distance with high probability, I'm going to actually get every good heuristic value that exists within my set of heuristics in an exponentially growing state space. And so what I'm going to see is that I'm going to occasionally see really good values, and sometimes I'll see bad values. But if I'm using the BPMX to propagate those values, then what's going to happen is I'm going to be able to propagate those values and basically not pay the cost of the places where I have inaccuracy, or the cost won't be large. And so what happens is I have a trade-off of I do fewer lookups to get a slightly less informed heuristic, but because sometimes I get very uninformed values, the actual cost will be only a small number of extra node expansions. So there's a journal paper that we wrote that looks at what is exactly the impact of looking at a random mix of heuristics. And there is some sweet spot where you should look up, if I have 20 heuristics, I might be able to look up, I should look up 3 of them, or whatever the value happens to be, and I'm going to get better performance than looking up all 20, even though all 20 gives me the most informed heuristic. The cost per expansion is very high. So we're trading off the cost per expansion with the number of node expansions. Okay. The other thing that we can be thinking about is, why did we get an exponential number of node expansions? And do we have to worry about this in practice? And what we can see here is actually, if we look at the formulas that are used to build this general case, what we can see is that actually this value is growing exponentially. If you go onto the web page and you play with inconsistent heuristics, you'll see on this generator, as you increase the problem size, that this grows exponentially. And it ends up to have an exponential number of node expansions. Given that these are all integers here, to have an exponential number of node expansions, we must have an exponential number of costs. So if we just have a polynomial domain, with a polynomial domain, we're going to we're going to be guaranteed to only having a polynomial number of node re-expansions. And so here we might be seeing something more akin to n squared or something like this. Could actually come out for A star for most of the problems that we're wanting to see in practice. And so I'm not going to go through the math here. It's in the journal paper. But basically, you can look at the minimum change in heuristic value. You can look at the maximum heuristic value in the state space, and you can use this to figure out how many times every node could have its heuristic reduced, and that's going to give you a bound on how many node expansions you can have. And so, so this gives us inconsistency as it stood, sitting around 2010. I think 2010 is around when we wrote a journal paper that went over this case and sort of presented this, the use of BPMX, looked at sort of good and bad ways that BPMX could be applied, looked at the best case and worst case of BPMX, in this case being n squared, in other cases being, that it could sort of have exponential savings or arbitrarily large on any given problem instance. We can make, for any number that you want, any constant, I can get rid of that number of node expansions. And so, assuming that if the problem's growing exponential, we can get an exponential reduction in node expansions. So this is nice, but this doesn't get us something like BPMX, and even algorithm B, it still got us down to this n squared. And what we'd like to get down to is something better than that, and we're going to be doing that in the next lectures.